For years, the AI industry has followed one simple rule. If you need more speed, buy more GPUs. Build larger data centers. Use more electricity. Spend more money. But what if the biggest problem in AI isn't computing power at all? What if the real bottleneck is something almost nobody talks about? A research team at Peking University has demonstrated an experimental system that approached AI inference in a completely different way. Instead of building a faster processor, they redesigned how information moves between processors, using light instead of conventional electrical connections. In their specific benchmark, the result dramatically outperformed a much more powerful GPU on the same task. The question is not whether GPUs are obsolete, but whether this points toward a new direction for AI computing. Let's decode the story. Modern AI chips are engineering marvels. A single high-end processor can perform trillions of mathematical operations every second. But surprisingly, raw computing power isn't always what limits performance. Before an AI chip can perform any calculation, it first has to receive data from memory, from another processor, or from a different stage of the AI model. Every transfer takes time, and every transfer consumes energy. Engineers often describe this challenge as the memory wall. As AI models become larger and are distributed across multiple chips, processors spend an increasing amount of time waiting for data instead of performing calculations. Even thousands of powerful GPU cores can sit idle if the information they need hasn't arrived yet. The traditional solution has been straightforward. Build faster memory, increase bandwidth, add more GPUs, improve cooling systems. But those improvements still rely on electrical signals traveling through copper connections. As more data moves through those pathways, resistance generates heat, energy losses increase, and communication delays become harder to avoid. Eventually, adding more computing power delivers smaller gains because moving information, not calculating it, becomes the limiting factor. Instead of asking how to build a more powerful chip, the researchers asked a completely different question. What if we could almost eliminate the waiting? Their answer wasn't another GPU. It was an entirely different way of connecting processors, one that uses light to keep data flowing almost continuously between specialized chips. And that single idea may be the most interesting part of this breakthrough. So, how did the researchers tackle this problem? Instead of building one enormous processor, they divided the AI model across 5 programmable chips, known as FPGAs. Unlike traditional processors designed for general-purpose computing, FPGAs can be configured for specific workloads, allowing engineers to optimize how data moves through the system. Each chip was assigned a single layer of a 5-layer AI model, creating a dedicated workflow rather than repeatedly loading different tasks onto the same processor. The most important innovation, however, wasn't the chips themselves. It was how they communicated. Rather than relying on conventional electrical connections, the researchers linked the processors using custom optical transceivers capable of transmitting data at 400 gigabits per second through an optical switching system. Light carries information with lower signal loss over distance than high-speed electrical connections, helping reduce communication delays between processors. Think of it like an assembly line. Instead of one worker completing every step before starting the next product, each worker performs one task continuously while passing the result to the next station. Once the pipeline is full, every worker stays busy and finished products emerge in a steady flow. The researchers applied the same principle to AI. As one FPGA completed its assigned layer, the data immediately flowed to the next chip through the optical network, allowing all 5 processors to work simultaneously with very little idle time. The benchmark results attracted attention. Using a previously trained 5-layer image processing model, the experimental system completed its specific inference task dramatically faster than the GPU used for comparison, despite having significantly lower peak computing performance on paper. According to the source material, the FPGA-based system achieved very high hardware utilization because it spent far less time waiting for data transfers. But it's important to understand what these results do not mean. This experiment did not demonstrate that FPGAs are universally faster than GPUs, nor did it replace the large-scale GPU systems used to train today's most advanced AI models. The benchmark involved a relatively small, pre-trained model performing inference on a specific dataset under carefully controlled conditions. Larger language models, complex training workloads, and different software environments may produce very different results. Even so, the broader implication is significant. The future of AI may depend not only on building more powerful chips, but also on designing smarter ways for those chips to communicate. As AI models continue to grow, reducing delays between processors could become just as important as increasing raw computing power. In the end, this research isn't simply about replacing GPUs. It's about challenging a long-standing assumption in computing. Sometimes the fastest system isn't the one with the most power. It's the one that wastes the least.